One of the most commonly asked questions at data science interviews is about overfitting. A recruiter will probably bring up the topic and ask you, "What's overfitting and how do we deal with it?" Fortunately, in this lesson, we'll address this issue, and you won't be surprised when it comes up. There are two concepts that are interrelated: underfitting and overfitting. They go together. Understanding one helps us understand the other, and vice versa. Okay. Broadly speaking, overfitting means our regression has focused on the particular data set so much it has missed the point. Underfitting, on the other hand, means the model has not captured the underlying logic of the data. It doesn't know what to do, and therefore provides an answer that is far from correct. Let's explain this with graphs, as it is both more intuitive and cooler. Here, we can see several data points. A good algorithm would result in a model that looks like this. It is not perfect, but is very close to the actual relationship. Okay, we can certainly say a linear model would be an underfitting model. It provides an answer but does not capture the underlying logic of the data. It doesn't have strong predictive power. Underfitted models are clumsy and have a low accuracy. You will quickly realize that either there are no relationships to be found or you need a different model. Alright, let's check an overfitted model. Here it is. Now that you can see this picture, we can say overfitting refers to models that are so super good at modeling the data that they fit or at least come very near each observation. The problem is that the random noise is captured inside an overfitted model. Obviously, we went through this concept outside the scope of logistic regression. That's because underfitting and overfitting are problems encompassing predictive analysis as a whole. But since we are in the logistic regression section, we'll explore a logistics regression overfitting problem. Imagine we have this model on a sample of 10 points. Now somebody gives us 100 other observations from the same population. We quickly realize that the relationship has nothing to do with what we had found. In real life, the case probably won't be as dramatic. For instance, our population data is likely to be distributed like this. Looks okay, but then all these points over here are misclassified because of the initial model. After quick examination, we realize that the real relationship is quite similar, but say a bit to the left. I'll stop now, as I believe you got the point. Now, underfitting is easy to spot. You have almost no accuracy whatsoever. Overfitting is much harder though, as the accuracy of the model seems outstanding. There is one popular solution to overfitting though. We can split our initial dataset into two: training and test. Splits like 90% training and 10% test, or 80-20, are common. It works like this. We create the regression on the training data. After we have the coefficients, we test the model on the test data by creating a confusion matrix and assessing the accuracy. The whole point is that the model has never seen the test dataset. Therefore, it cannot overfit on it. Cool. In the next lesson, we will test a model. Thanks for watching.